New cars today are packed with advanced engineering, lightweight materials, and high-efficiency engines, but that also means they're far less forgiving than older vehicles. Surprisingly, many serious cooling problems don't start with a major defect. They begin with small common coolant mistakes that most drivers never think twice about. These issues can build quietly, even in brand new cars, until overheating becomes hard to ignore. In this video, we'll break down 13 coolant mistakes that are often overlooked, explain why they matter so much in modern engines, and help you understand what to avoid before minor oversights turn into costly problems. This is widely considered one of the most destructive mistakes drivers can make when maintaining their cooling system. Modern engine coolants are not all the same. Each formula, whether traditional green, orange, blue, pink, or purple, is designed with a specific chemical package to match certain engine materials and manufacturing standards. Mixing incompatible types such as conventional green coolant with orange formulations or Asian blue coolant with Dex Cool can disrupt that chemistry. When incompatible coolants are combined, their additives can neutralize each other or react in unintended ways. The result is often thickened, fluid gel formation, or sludge. Once sludge forms, it doesn't stay suspended, it settles into the narrow passages of the radiator heater core thermostat and even the engine block itself. This restricts coolant flow, reduces heat transfer, and forces the system to work harder just to maintain normal operating temperatures. Engineering guidance and industry testing consistently show that mixed coolants can rapidly lose their corrosion-inhibiting properties, sometimes in a fraction of their intended service life. Without those inhibitors, internal metal surfaces, especially aluminum, are left unprotected. Corrosion can begin quietly attacking water pump seals, radiator cores, and gasket surfaces long before any warning light appears on the dashboard. One of the most dangerous aspects of this mistake is that the damage is often invisible at first. The engine may seem perfectly fine for months, even years, while corrosion and deposits slowly build inside the system. By the time overheating or leaks become obvious, the repair costs are often substantial. The solution? Just don't mix different types together. Always use a single coolant type that meets your vehicle manufacturer's OEM specification. If you ever need to change to a different formula, perform a complete system flush first. This extra step ensures chemical compatibility and protects your engine from long-term damage. Many drivers assume that once the cooling system has been flushed and refilled, the job is complete. In reality, that final fill is only the beginning of the process. During a coolant service, air inevitably becomes trapped in the radiator heater core hoses and engine passages. Once the vehicle is driven and the engine reaches operating temperature, those air pockets slowly rise and escape. As they do, the coolant level drops sometimes more than drivers expect. When this happens, the system may be left partially underfilled, meaning the engine is no longer fully protected. Even small amounts of trapped air can disrupt coolant circulation, reduce heat transfer, and create localized hotspots inside the engine. Over time, this can increase operating temperatures, place added stress on seals and gaskets, and raise the risk of overheating. Technicians often refer to this process as the settling effect, and it is especially common after do-it-yourself coolant flushes. Professional shops typically account for this by performing follow-up checks or using vacuum fill equipment, but many DIY services end without verifying the final coolant level after the system has fully stabilized. If the level is not corrected, air can be drawn back into the system during cooling cycles, compounding the problem. We suggest you recheck the coolant level after your first drive, then inspect it again after about 24 hours. Top it off as needed following the manufacturer's guidelines. Taking a few extra minutes to do this simple check can make the difference between a properly serviced cooling system and one that fails far sooner than it should. At first glance, using tap water in the cooling system may seem harmless. After all, it's clear, readily available, and often considered clean. Over time, however, it can be extremely damaging. Tap water contains dissolved minerals such as calcium, magnesium, iron, and other trace elements. When exposed to the high temperatures inside an engine, these minerals separate from the water and form hard-scale deposits along the radiator fins, engine coolant passages, and heater core. This buildup acts much like plaque in human arteries. As the deposits thicken, they restrict coolant flow and insulate metal surfaces from direct contact with the coolant. Heat can no longer be transferred efficiently, forcing the engine to operate at higher temperatures, even under normal driving conditions. As the system struggles to compensate, the risk of overheating increases and corrosion accelerates from within, often without any immediate warning signs. Mineral-rich water also interferes with the chemical balance of modern coolants. Corrosion inhibitors are designed to work in a controlled environment, and the presence of minerals can reduce their effectiveness. In some cases, scale buildup can even damage water pump seals, clog narrow passages, and shorten the life of the radiator and heater core. For this reason, the safest approach is to follow the manufacturer's instructions precisely. Coolant should be mixed with distilled water, typically in a 50-50 ratio unless otherwise specified. Distilled water has been purified to remove minerals and contaminants, allowing the coolant's additives to perform as intended, protecting against corrosion, preventing scale, and maintaining proper heat transfer. At roughly $1 per gallon, distilled water is a minor expense, yet that small investment can help prevent radiator replacements, water pump failures, and cooling system repairs that often cost hundreds or even thousands of dollars. The word universal sounds reassuring until it quietly begins to damage your cooling system. Modern engines are far more sensitive to coolant chemistry than many drivers realize. Today's vehicles, especially those with aluminum engine blocks, cylinder heads, and radiators, are engineered around very specific coolant formulations. These formulas are often silicate-free or use carefully balanced additive packages designed to protect lightweight metals, seals, and gaskets over long service intervals. So-called universal coolants attempt to cover many applications with a single blend, but that compromise can come at a cost. Some rely on additive chemistries that are not fully compatible with certain alloys or sealing materials. When the chemistry is even slightly wrong, corrosion protection weakens, rubber seals can harden or swell, and internal components begin to wear prematurely. One of the most common victims is the water pump. The pump depends on proper lubrication and chemical stability from the coolant itself. When incompatible additives are present, pump seals can deteriorate. Bearings can wear faster and leaks may appear far earlier than expected. Industry testing and manufacturer guidance consistently show that using the wrong coolant formulation can significantly shorten water pump lifespan, increasing the risk of overheating and cascading failures throughout the cooling system. Fixing this is actually very easy. You just need to pay attention and read the label carefully. If the coolant does not clearly state compatibility with your vehicle's make and specification, don't take the risk. An OEM-approved coolant may cost a little more up front, but it preserves seals, protects aluminum components, and can prevent repair bills that run into the thousands. Have you ever noticed a gurgling or sloshing sound coming from behind the dashboard after changing your coolant? That noise is more than just an annoyance. It's a clear warning sign that air has become trapped inside the heater core or cooling passages. And in a cooling system, trapped air is always bad news. Air pockets interrupt the normal flow of coolant, preventing it from circulating evenly throughout the engine. Unlike liquid coolant, air cannot carry heat away efficiently. As a result, localized hotspots form in areas where metal is no longer in direct contact with coolant. These hotspots can cause uneven engine temperatures, placing excessive thermal stress on cylinder heads, gaskets, and seals. Over time, repeated heat cycling in these areas increases the risk of gasket failure, warped components, and sudden overheating, sometimes even when outside temperatures are mild, and the vehicle appears to be operating normally. In many cases, the temperature gauge may not immediately reflect the problem, making it especially dangerous. What to do in this case is to bleed the cooling system after any coolant service. Use the manufacturer-recommended method, such as a bleed screw vacuum fill or a spill-free funnel. Many modern vehicles are designed with dedicated bleeder valves near the thermostat housing specifically for this purpose. Skipping this step may seem minor, but it can cause an otherwise healthy engine to overheat on a perfectly cool day. Many drivers believe coolant lasts forever. Unfortunately, that assumption couldn't be further from the truth. Even so-called long-life antifreeze is a consumable fluid. Over time, heat cycles, oxygen exposure, and normal chemical reactions slowly degrade the coolant's additive package. Corrosion inhibitors are depleted pH balance shifts, and the fluid can become increasingly acidic. Once this breakdown begins, the cooling system starts to suffer quietly from the inside out. Acidic coolant attacks metal surfaces, weakens gaskets, and shortens the lifespan of sensors, radiator cores, and heater components. In aluminum-intensive modern engines, this process can accelerate electrochemical corrosion, gradually eating away at internal passages long before any external symptoms appear. By the time leaks, warning lights, or overheating occur, the damage is often already well underway. Another overlooked factor is contamination. Over the years, microscopic metal particles, sealed debris, and mineral traces accumulate in the coolant. These contaminants further reduce heat transfer efficiency and place extra stress on the water pump and thermostat, compounding wear across the entire system. This brings us back to the most fundamental principle of car maintenance: coolant must be replaced on schedule. Most manufacturers recommend a coolant change every 3 to 5 years, or approximately 50,000 to 100,000 miles, depending on the coolant formulation and vehicle design. Ignoring this interval doesn't save money, it simply delays maintenance until it becomes a repair. If you've purchased a used vehicle and don't know when the coolant was last changed, the safest assumption is that the service is overdue. Starting fresh with the correct coolant restores corrosion, protection, stabilizes operating temperatures, and helps ensure the long-term health of the engine and cooling system. You see, that small plastic or metal cap on your radiator or coolant reservoir plays a far bigger role than most drivers realize. It isn't just a cover, it's a precision pressure regulator. By sealing the cooling system and maintaining internal pressure typically in the range of 13 to 16 psi, depending on the vehicle, the cap raises the coolant's boiling point significantly. This allows the engine to operate safely at higher temperatures without the coolant boiling over. When the cap is in good condition, it keeps the entire system stable. But over time, heat cycles take their toll. The internal spring can weaken, rubber seals can harden or crack, and the cap may no longer hold pressure consistently. When that happens, the system begins to lose pressure without obvious signs. Coolant may boil at a lower temperature vent through the overflow or slowly escape sometimes without triggering a warning light or causing the temperature gauge to spike. This hidden loss of pressure is especially dangerous because it creates a false sense of security. The engine may appear to be running normally, while localized boiling and coolant loss quietly reduce cooling efficiency. Left unaddressed, this can lead to overheating, warped components, and damage to gaskets and seals. So what should you do? It's fairly simple. Inspect the coolant cap regularly and replace it about every 5 years or sooner if you notice cracks, leaks, or white residue around the seal. It's a simple, inexpensive part, often under $10, that can help prevent repair bills running into the thousands. When it comes to coolant, more is not better. The cooling system is designed to operate within very specific volume and pressure limits. Overfilling the reservoir leaves no room for thermal expansion as the engine heats up. As coolant expands, the excess volume has nowhere to go, forcing fluid into overflow hoses, or in more severe cases, pushing past seals, stressing hoses, or lifting the reservoir or radiator cap. This excess pressure doesn't just create a mess, it can weaken components over time. Hoses may swell, clamps can loosen, and seals that were once perfectly sound may begin to seep. In some vehicles, repeated overfilling can even damage the reservoir itself, causing cracks or deformation from constant pressure cycling. The imbalance doesn't stop when the engine cools down. As temperatures drop and the coolant contracts, the system may draw air back in instead of coolant. This introduces air pockets that disrupt circulation, reduce heat, transfer efficiency, and interfere with proper temperature regulation. Air trapped in the system can also lead to erratic heater performance and increase the likelihood of localized hotspots inside the engine. So the tip here is to fill the coolant reservoir only between the minimum and maximum marks, exactly as specified by the manufacturer. Staying within this range allows the system to manage pressure correctly, and protects it from unnecessary stress. The thermostat may be small, but it plays a critical role in engine health. Its primary function is to regulate when coolant begins circulating through the engine and radiator. It opens at a precisely calibrated temperature, typically around 195 degrees Celsius, for most modern vehicles, allowing the engine to warm up quickly, then maintain a stable operating temperature for optimal efficiency emissions, control, and component longevity. Over time, however, thermostats are exposed to constant heat cycles, pressure changes, and chemical exposure from the coolant itself. As they age, internal components, such as the wax pellet spring or valve mechanism, can wear out or become contaminated with deposits. When this happens, the thermostat may begin to stick. A thermostat that sticks open prevents the engine from reaching its ideal operating temperature. This can result in reduced fuel economy, increased emissions, sluggish cabin heating, and accelerated engine wear due to extended cold operation. On the other hand, a thermostat that sticks closed is far more dangerous. In this failure mode, hot coolant becomes trapped inside the engine block, preventing heat from escaping. Engine temperatures can rise rapidly, leading to overheating before the driver has time to react. This is why many technicians refer to a failed thermostat as a silent engine killer. The engine may appear to operate normally for months, until one day the temperature gauge suddenly spikes with little warning. By then, the risk of warped components, damaged gaskets, and costly repairs is significantly higher. As a responsible owner, replace the thermostat proactively, usually every 5 years, or around 60,000 miles, especially on aging vehicles. Always choose OEM or reputable high-quality brands such as Stant or Gates. Low-cost thermostats often fail prematurely and can cause far more expensive damage down the road. This is one of the most tempting and ultimately most damaging shortcuts in cooling system maintenance. Stop leak products are often marketed as quick, affordable solutions for coolant leaks, and in very limited cases, they may slow or temporarily seal a small seep. The problem is that these additives don't know where the leak is. Once poured in, they circulate through the entire cooling system, not just the damaged area. As they travel, stop leak compounds can deposit residue along the radiator tubes, heater core, water pump passages, and other narrow channels designed for precise coolant flow. Modern cooling systems are especially vulnerable because their passages are smaller and more complex than those in older vehicles. Over time, this residue can harden and accumulate, restricting circulation and reducing the system's ability to shed heat efficiently. The long-term effect is gradual but serious. Coolant may still move but not fast, or evenly enough, allowing heat to build in localized areas of the engine. This leads to higher operating temperatures, increased thermal stress on components, and inconsistent cabin heating. Many technicians liken this buildup to cholesterol in arteries. It doesn't cause an immediate failure, but it slowly narrows critical pathways until the system can no longer perform as designed. There's also another risk drivers often overlook. Stop leak products can interfere with sensors, clog heater cores entirely, or contaminate coolant so severely that a full system flush or even radiator replacement is required. What began as a minor hose seep can escalate into a multi-thousand-dollar repair involving overheating issues that are difficult to diagnose. So if you notice a coolant leak, locate the source and repair it properly, whether it's a hose clamp seal or gasket. Temporary chemical fixes often turn a minor repair into long-term damage, costing far more in the end. The water pump is truly the heart of the cooling system. Its primary responsibility is to keep coolant circulating continuously through the engine radiator and heater core. When that circulation is interrupted, heat has nowhere to go, and engine temperatures can rise far faster than most drivers expect. What many people don't realize is that water pumps almost never fail without warning. In the vast majority of cases, they provide clear, though often subtle signals well before a complete breakdown occurs. One of the earliest signs is a small coolant leak beneath the engine. This fluid may appear green, pink, orange, or blue, depending on the type of coolant used. These leaks often originate from the pump's internal seal and escape through a small opening known as the weep hole, which exists specifically to signal impending failure. Another common warning sign is noise. A failing water pump may produce a high-pitched whining, chirping, or grinding sound that changes with engine speed. This usually indicates worn internal bearings, which can deteriorate rapidly once noise becomes noticeable. In some cases, you may also see rust stains or a chalky white residue forming around the pump housing, evidence of slow coolant seepage and corrosion. Ignoring these warnings can be costly, especially on vehicles where the water pump is driven by the timing belt. In these designs, a seized or wobbling pump can damage or derail the belt, potentially leading to severe engine damage in a very short period of time. Even on engines with belt or chain-driven accessories, a failed pump can cause sudden overheating that leaves little time to react. Industry data from roadside assistance providers consistently shows that a significant share of overheating-related breakdowns are linked to water pumps that were already failing but went unaddressed. In many cases, the symptoms were present for weeks or even months beforehand. Next time you see a warning sign pop up, treat early warning signs seriously and replace a suspect water pump before it turns a manageable repair into a major engine problem. This is a surprisingly persistent myth that coolant is only necessary in hot weather. In reality, coolant serves multiple critical functions that protect your engine year-round. It is not just an antifreeze, it is also an anti-boil fluid, a lubricant for cooling system components, and a long-term corrosion inhibitor. During cold weather, coolant prevents the liquid in the engine from freezing and expanding, which could otherwise crack engine passages, damage the radiator, or rupture hoses. But just as importantly, in warm and moderate conditions, coolant raises the boiling point of the system, allowing the engine to operate safely at higher temperatures without vaporizing the fluid. Plain water, by comparison, boils far more easily and offers virtually no corrosion protection. Modern engines are especially vulnerable without proper coolant because they rely heavily on aluminum blocks, cylinder heads, radiators, and heater cores. When the antifreeze concentration is incorrect, or when coolant is diluted with plain tap water, galvanic and electrochemical corrosion can begin to attack these metals. This process can occur quietly, sometimes even while the vehicle is parked, slowly eating away at internal passages, weakening seals and contaminating the cooling system with corrosion byproducts. Coolant also contains additives that lubricate the water pump seal and protect rubber hoses and gaskets from drying out or cracking. Without these additives, components may fail prematurely, leading to leaks and overheating that seem sudden but are actually the result of long-term neglect. For most vehicles, the safest approach is to maintain a 50-50 mixture of coolant and distilled water throughout the entire year, unless the manufacturer specifies otherwise. This ratio provides an ideal balance of freeze protection, boiling resistance, corrosion, inhibition, and heat transfer efficiency. In extremely cold climates, concentrations of up to about 60% antifreeze may be acceptable to improve freeze protection. However, exceeding that level can reduce the coolant's ability to transfer heat and may actually raise operating temperatures, doing more harm than good. Suppose your engine overheats just once. You identify the immediate cause, make the repair, refill the coolant, and drive away thinking the issue is behind you. Problem solved, right? Unfortunately, overheating leaves behind more than a temporary temperature spike. When coolant is exposed to extreme heat or reaches its boiling point, its chemical balance begins to collapse. The corrosion inhibitors that protect the engine are depleted, and the fluid can break down into acidic compounds while carrying microscopic metal particles released from internal components. If you simply top off the system or refill it without a proper flush, those contaminants stay trapped inside the radiator engine block, heater core, and narrow coolant passages. Over time, this acidic mixture slowly attacks aluminum fins and internal surfaces, eroding protective layers and accelerating corrosion from the inside out. Because this process happens gradually, drivers often don't notice a problem until cooling efficiency drops, temperatures creep higher under normal driving, or leaks begin to appear. You want solution. After any overheating incident, perform a complete radiator and cooling system flush, using distilled water followed by fresh coolant mixed to the proper ratio. While you're there, inspect hoses and clamps carefully. Excessive heat can permanently weaken rubber components. Experienced technicians often note that contaminated post-overheat coolant takes on a muddy or brownish tint, a clear warning sign that it must be replaced to prevent ongoing corrosion. When you look at these 13 coolant mistakes together, one thing becomes clear: engine problems often don't start suddenly, they build up quietly through small oversights. Modern vehicles leave little room for error, and cooling systems are less forgiving than ever. Paying attention to the basics can help reduce unnecessary stress on your engine over time. Have you ever experienced overheating or coolant issues on a newer car? And which of these mistakes do you think is most commonly overlooked? Share your thoughts in the comments below. Lastly, this video is based on public sources, vehicle manuals, and automotive research for educational purposes, only, not to promote any brand. Always verify information, follow your vehicle's recommendations, and make informed maintenance decisions. Thanks for watching, and see you in the next video.